Okay, so in one of our last parts here, we're going to talk about 2D sprite rendering. So in this image, you're going to see on the left-hand side, you have an old Sega Genesis game called Shining Force, and on the right you have a more modern 2D game, Terraria, written for PC in the DirectX 9 era. Probably don't know the exact year, but mid late 2000s, I would say. So the interesting part about these two games is that they look very similar, right? They're both 2D games. Obviously, there does appear to be more. You get to see more a little bit on the right than you do on the left. But there's a big age gap between the two games. And interestingly enough, there is a significant difference in how they are executed from a technical standpoint. Okay, so these two games are actually rendered or drawn in quite different ways. Okay, the underlying technology below them is is fundamentally quite different. All right. So what do I mean by that? Even though they look the same. Well, the question here is, how many real 2D games have you actually played, right? Because all modern 2D games, almost every modern 2D games, is actually running on 3D hardware, all right? So that game Terraria on the right is actually rendered using polygons and textures. Yes. So if we were to take a look at any one of these sprites being an older term for a set of pre-made raster data, what they are actually are polygons with textures on them. All right, and there are actually some advantages to doing this, using 3D geometry with texturing data to draw 2D systems. Even though these polygons and textures were meant for 3D, you can still use them in 2D. And we'll talk later on as to why there are significant advantages to doing that. And you get, essentially it boils down to, you can use the hardware with this system where you otherwise couldn't. You can use customized 3D hardware, whereas if you didn't use this polygons textures, you couldn't make use of it. So there's a big difference from these older games, though, right? Like the Shining Force here on the left. These were actually not rendered using polygons or textures or anything like that in any modern sense. These are actually real 2D games using real 2D hardware specifically designed to do 2D. All right. And I do mention some of these advantages here for using the 3D stuff. But let's just focus on the 2D stuff for now. So the pure 2D systems use something called a Blitter chip, because they didn't use 3D hardware. They didn't have 3D hardware. So this Blitter chip was a chip that worked alongside the main processor, and it could work in tandem with it. And it efficiently lets you transfer image data or raster data from one raster area to another, right? Or offline rasters. So you have some pixel data that you want to eventually transmit to the display. So these Blitter chips allow you to do that. So that's quite a way from using polygons. And we'll eventually talk about polygons in 3D. But to do classic 2D, you don't need anything like this, right? This is specifically more of a modern approach to doing 2 dimensions. And in fact, a lot of systems, like maybe you used like an engine like Unity, or you've used Unreal, and they have 2D systems in play. All of those 2D systems underneath the hood are doing 3D calls. Okay, they're using a 3D API. Because it lets them do, because you can rely on the hardware then and make use of it, and it's very efficient to do so, to utilize 3D hardware. Because you got to imagine, if you have a system designed to do pure 3D system red drawing, then it's not going to have too much trouble flattening things out and making them in 2 dimensions, and it really isn't. But let's focus on older techniques here, so older 2D rendering. So blitting, by the way, the letters BLIT, B-L-I-T, they stand for block image transfer. Okay, so the idea here is we're copying pixels. We're doing a direct transfer of a block of pixels to one area. So this would be our block right on the right-hand side in ROM. So you all probably know what RAM is, right? Random access memory. But ROM stands for read-only memory. So this is memory you would usually find on older console game systems like the Sega Genesis, the Super Nintendo. More modern handheld systems had it, like the Game Boy Advance. The most recent console to really use cartridges has been a long time. The Nintendo 64 used cartridges, and all these cartridges had ROM. So essentially what we were doing when you plugged in this cartridge, this game cartridge, is you were actually adding hardware to your system. You're actually adding a set of chips. And that's why these older games, if you've played any of these older games, they don't have these long load times that modern games do. And you're not constantly sitting there staring at loading screens. In fact, they're almost instantaneous, right? The loading is almost instant there, or if not instant. And that's because essentially everything is already in memory. Everything is already in this ROM. So imagine if everything you needed for your program was just already there at a particular memory address. And that's the big advantage of using ROM. So why are we still using ROM? Sounds great. I mean, I think, you know, if it was affordable, people would like, oh, I don't want to deal with load times. Well, yeah, but here's the thing. Even back then when they were selling these cartridges, games were more expensive. Not necessarily that they were super expensive to develop, because you didn't need as many artists, you didn't need as many resources as you do nowadays. But the games themselves had a physical cost because you were actually selling a cartridge with chips in it, as opposed to a couple cents CD or printed medium. And these days we just download things digitally. So there's just whatever the cost of your bandwidth is, that's what you're paying to get the game. It's just through digital distribution. So this ROM had some significant advantages there. So in these 2D systems, you had access to this ROM, which had this offline, this raster information, these pixels or bitmap images, which are these collections of pixels. And the idea is we want to transfer from the ROM onto the display. All right. Now, we're kind of oversimplifying things. These older devices, right? They had a far more limited memory footprint than we're used to on our laptops or on modern computing. So they definitely had more efficient ways of doing this. But just for the basic concepts, we're going to think about the process of transferring from this ROM area onto the image. So we're going to assume we have a set of information here for the raster on the left for our screen, and we're going to have a set of information here on the right for our ROM that we're going to read from. So that's what would happen with this splitter hardware. Transfer an image, as you can see, onto the display. And this would happen for the many different tiles that you had. And then you had many tile-based games here, which was just redrawing all these bitmaps. Okay. So our challenge here, and what you will be challenge that you'll have in your lab, is how do you recreate the situation? And first of all, what would we need to know to recreate the situation? Well, let's start with what we have here. We have two arrays, right? We have an array for the raster, what we're going to see on screen. So I'm going to highlight it here. So we have this array, and we have the ROM array as well. So we need a pointer to both arrays. What we also need to know is we need to know, where are we going to be drawing? Well, I'm going to be drawing right here, right? This top left corner. That's where the pixel transfer is going to start. Actually, let me highlight that a little differently. So we'll be drawing right there. So we need a destination draw location on the raster, right? We need to know that as well. Oftentimes, if you are going to loop through and copy information, oftentimes this information is not always stored in a two-dimensional array, though it can be. Many times you'll find image information like this stored in a one-dimensional array. All right. So if it is all in singular block in a one-dimensional array, you're going to need to know the dimensions of your array, whether that be 2D or 1D. You're going to need to know those dimensions. And we have two distinct sets of dimensions here, right? We have the width of the raster. We have the height of the raster as well. And we have the width of our source data and the height of our source data. So we need to know those items. So now we have almost everything we need, but if you look closely, you can see we're transferring this cyan block over here to the left. So not only do we need to know the arrays, the dimensions of the arrays, and where we're going to be drawing to, but we need to know particularly how much of this source data, this ROM, that we need to be reading from. So we need to know the dimensions, well, not only the starting location of that block over here on the right, but its dimensions. So we need to know about this rectangle here. We need to know its left-hand side. We need to know its right-hand side. We need to know its top, and we need to know its bottom if we're going to effectively copy exactly those pixels over to the left. So there's just some examples. Now if we have that information, we should have everything we need to copy that. So here's a example. So if you were to write a function to duplicate this behavior, right, assuming you had this information available to you, this is the type of information you're going to need to know. You're going to need a pointer to the source array, right? This would be your pointer to the source array. You need a pointer to the destination array, or destination screen array. That would be our screen array right here. We need to know the image dimensions, the source image dimensions. So we need this, width and height. We need our destination width and height here. So we need to know those. And we need the subrectangle. Let's highlight that in a different color so we don't get too messy here. Let's do green. So we need this rectangle here. Actually, green was a bad choice. It already is green. I'll just paint it in here. So we need to know this whole area over here, that green zone. And lastly, right, we need to know where it's going. Where it's going. Let me paint this actually purple so you can see it. You know, this area. It's left, right, top, bottom. We need to know that. And those are just single values, right? Amount from the left, amount from the top, amount from the right, amount from the bottom. And we also need to know where this is going. It's going right there in our case. Okay. That's just an XY location. All right. We can call that the drawing position, where it's going to be drawn. Okay. So this will give you, this is what your function arguments should look like to draw a bullet function that will copy from one area to another. It's very important to keep in mind that the source image array is different than the screen array. The dimensions are different, and at different times you might need to use different values. So if you accidentally interchange these values, that can lead to some serious problems. So don't do that. That would be bad. So make sure that you use the source image array when you're working with a source image array, and use the destination array when you're working with a destination array, that you use the right values to go back and fro. All right. So here's another little diagram of Blade hardware, how you might do this transfer. Okay. So once again, we have our source image data. Looks like some low resolution crystals over here, or gems, and we want to draw it over to the screen. So on this screen, you also see there I have this scan line here. You won't be dealing with a scan line when you work with this. You'll be just dealing with singular arrays. But these old hardwares like this didn't actually have a whole frame buffer, didn't have memory for the whole frame buffer. So instead, what would happen is during blidding, it would do the transfer, and the scan line would move usually to the right and down, and it would collect and pick the pixels as it went, and it went at a particular speed, like 30 hertz or what have you, 30 times a second. And then it would fill in the pixels as appropriated, as specified by the blidding chip. But since we're not dealing with these, we're actually writing code for these older consoles, we actually will have a full frame buffer, so you'll have a whole memory area to copy your pixels into, and that's what you'll be doing. Okay. What else to say here? Not much. Okay. Talked about that. All right. So last thing to talk about is what you'll be doing in lab. You'll be using a header and CPP file called the raster surface. All right. Now we're going to actually cover working with the raster surface. That's one kind of be one of the first things we do. Is I'm going to show you that during lecture. When we meet in class, I'm going to show you how to actually work with that directly, so there's no confusion there. That being said, it's actually extremely simple. It's just a header and CPP file. Now, the reason I'm even providing, you're probably wondering, well, all we're doing is copying pixels. Why is it that we need something? We even need something from you to do this? Well, on an old console like the Sega Genesis or Super Nintendo or Game Boy Advance or something like that, a Game Boy Advance, you had direct access to copying data back and forth from memory areas, and you had much more direct access to working with these things because they were designed to do that. Now, on a computer platform, on PC, we have a lot more things in the way from you and the display. So not only are you working in an OS, right? Your actual visual display is connected to a video card, right? And that video card has something called a driver, which communicates from the actual video card itself. It's to the operating system, so it's kind of like a middleman that sits between the two. And the reason you have that is because there's many different types of video cards, right? So you need some sort of connection between the manufacturer and the operating system vendor to have that connection between the two. So to get to the actual raster, to display stuff up there, you would have to go through the OS, talk to the driver. The driver's got to communicate to the video card. You'd have to figure out to get to the actual memory area. It would take jumping through quite a few hoops. So the goal here isn't for you to learn necessarily how to do that, how to jump through these hoops to get the raster. We're really focused on the fundamental basics here of how this stuff, how just drawing the graphics and works, the theory of it. So to that end, I provided this raster surface.h and CPP. You're more than welcome to go look in the code and see what it does. That's one of the big things with this class. There's no black boxes in this class. So we're going to be very transparent with you. So what this class will allow you to do is just take a block of pixels that you allocate and copy it to the screen. And then you can just edit that block of pixels, and then you'll get visuals. So it's going to be very direct. Now the thing is, it's not like Unity or these other programs. There's no hand holding here. There's no, all these functions they're not provided for you. It's just going to be you, raw arrays of color data, and your wits and what you've learned in a lecture, right? So that's going to be it. So it's going to be a lot of fun. It's going to be very direct, right? So, and interestingly enough, you'll actually be writing console programs. So you'll be writing Win32 console applications like you did in your first programming classes. So that's going to be fun, going back to that. So you can actually use things like cout and stuff too if you want to like do error checking and whatnot. So that'll be nice. All right. Yes, and yeah, we'll have, by the time you watch this video, we'll likely have already done this code along. So I'll show you how to use the basics of the raster surface. Not that it's hard to use by any means, but I do want you to have less confusion about how this system works. Okay, so yeah, that covers it for your first assignment. Here you see I have listed your required reading assignment. These are very helpful. They help prepare you for the next set of material. And it's also very important that from now on you do start bringing graph and line paper and pencil and a handheld calculator to class, so we can do exercises, so you can see how these things work, and we can kind of buckle down any issues you might or confusion you might have from these lesson plans. Okay, all right. So if you notice I have these reading assignments, what am I asking you to read? This is a book from the syllabus that's listed. If I don't list specifically what book I want you to read from, I want you to read from Fundamentals of Computer Graphics. This book is listed in the syllabus. Okay, you can find your book on Safari. All right. We are doing, and the one that up there is the 3rd edition. This particular chapter I want you to read from the 2nd edition. I give you a little PDF in today's handout, and that's where you'll find that. But other than that, you will always want to use the 3rd edition of the book, which should be on Safari, called Fundamentals of Computer Graphics. Okay, and that is it for today's lesson.